Hello everyone. Today we are going to continue with what we have been doing so far, continue from dot products and talk about orthogonalization and things dealing with orthogonality. So, okay, let's start. So um Here we are going to discuss in general what are orthogonal and orthonormal sets. So let's recap a few definitions first. So we discussed orthogonal vectors when we talked about dot product and so let's recap what it means. Two vectors are orthogonal if the dot product is 0. So in that subsection, I mentioned that orthogonal vectors are sort of like a generalization of perpendicular vectors. So yeah. All right. So it's an extension of lines being perpendicular with each other. We're extending that concept to vectors. So when we extend it to vectors, we call the vectors that are perpendicular to each other orthogonal. So other than that, we need a few important definitions that in this section. So let's recall the definition of a span. A span of a set is going to be the set of all linear combinations of a vector. So that's going to be written as the span of the set of vectors. And in terms of set notation, the span of a set of vectors is described as the linear combination of all the vectors. So all these numbers, the scalars, are real numbers, and what we are taking is what this essentially means is we have all the set of vectors that we can construct by essentially multiplying any one of these vectors by any number and adding these combinations in whatever way that you want. So this entire collection is going to be called the span. And something that we need to remember is that this span forms a subspace of Rn. We have also discussed what like the idea of subspaces and what they are. So a subspace of Rn is going to be a set which contains 0, it's closed under addition, and it's closed under scalar multiplication. So there are three conditions, and we also learned the subspace test, right? Which allows us to determine whether any given subset is also a subspace. So if any of that's like sounds like Greek to you, we did that under subspaces and bases. So you can go check out this subsection or the video related to that. Okay, so let's describe so we have covered the span and covered the idea of subspaces. So now let's describe the span of these two vectors given. So going back to the definition, as I've written here, the span of these two vectors are going to be the set of all linear combinations of these vectors. And we discussed this example in the subsection called span. So I'll go through this briefly, but if you want more details, you can go back to that lecture video. So we can see that any linear combination of these two vectors yields a vector where the last component is 0. That's what this essentially means. And that's because if I take any number C1, any number C2, multiply C1 to this vector, I will get C1, C1, 0 plus 3C2, 2C2, 0. So when I add these two, regardless of what the constants are, I'm always going to get C1 plus 3C2, C1 plus 2C2, and 0. The last component is always a 0. That tells you that any linear combination of these two vectors is going to be on the xy plane. So it's going to be on a horizontal plane in our 3D space. So yeah. And then we can also show that every vector can be written as a linear combination of u and v. And this is how we can do that. If we are given a vector on the xy plane with the x component x, y component y, the coefficients will be given by these two terms, and thus this will be the C1 and this will be the C2 that we have in this definition here. So that will this means that we can write this vector here as a linear combination of these two. Okay, cool. The idea behind this is solving systems of linear equations, but I'm pretty sure we went through a very similar example under a span. So yeah, if you're concerned about the details, you can go take a look at it in that subsection. Okay, so the span of a set of vectors is what we call a subspace because it inherently satisfies the three conditions that I talked about. And another important thing that we talked about is linear independence. And this revolves around sets of vectors also. So if you have a set of non-zero vectors, it is said to be linearly independent if no vector in that set is a span of other vectors in that set. So let me just go back to the linear independence. All right. So the definition that we used is a bit different, but what they're describing here is just so that we know is that yeah, maybe uniqueness is not so much, but yeah, I think it's under this equivalence relation. So theorem 4.66, they tell us that if it's linearly independent, no vector is in the span of others. So these are equivalent. So we have proved that. So they're using that as an alternative definition. They're not using the original definition, which is this. But the idea is the same. So now we know what does linear independence mean. We want to show that this set is linearly independent. That means we want to show by definition, right? We want to show that if we have this system of linear equation, that each AI is 0. If you're not sure why this is a system of linear equations, again, we discussed this under this topic. So you can go check out that video. And but I wrote the gist of it over here. So if we want to show that this is linearly independent, that means I want to show that the solution to this equation is going to be C1 equal to 0, C2 equal to 0, and C3 equal to 0. So I need to show that this system has only one solution, and it's the trivial solution. So by the different algebraic manipulations that I did over here, this is just simple matrix multiplication and matrix vector multiplication. We get the augmented matrix, and from here we know how to solve the system of linear equations. So this is where the system comes from. So we have to show that the solution of this system is going to be the vector 0, 0, 0, 0, and then we know that's linearly independent. And that's what's done in this example. All right. And we also covered the basis, right? So if we have a subspace V, this set is a basis for V. That means every vector in V can be described as a linear combination of this if two conditions hold. First, the span of this set is equal to this entire space. So essentially, the span of some finite number of vectors is equal to this infinite dimensional space. And secondly, this set is linearly independent. So there are two conditions that needs to be satisfied. So just as an example, the vectors from this example, we established that it's linearly independent, and they also span the xy plane. So these two vectors are going to be the basis of the xy plane in Rn. Okay. Now let's look at this particular example. So again, the definition of orthogonal vectors, by definition of orthogonal vectors, two vectors are orthogonal if their dot product is 0. And what happens if a vector is orthogonal to a spanning set? of Rn. So let's say we have a subset, a set of vectors, and let's say we consider the span of that particular set. So all linear combinations of that set. And now we want to ask ourselves, if let's say for every vector in this set, my vector u is orthogonal to it, that means u dot xj is equal to 0. I'm using j as a subscript here because I want to show that if I pick any j equal to 1, j equal to 2, or j equal to k, I would get u dot xj equal to 0 for all j. Now, what type of vector is u? So, because of the fact that u is in Rn, and Rn is in the span of this set of vectors, and what does span means? This means that everything in this collection is a linear combination of this k number of vectors. That means because u belongs to Rn, which is the span of this, logically u can be expressed as a linear combination of these vectors. So that's why we can write u as a linear combination of vectors from x1 to xk. And then we're going to use a trick over here. And this trick is common whenever we have orthogonal vectors, because this property here actually makes things really beautiful. Like it simplifies things a lot. So using this property we learned in the dot product subsection, I'm going to replace one of the u's with the linear combination. I'm going to use distributive properties, and by the hypothesis that we have in our statement, we have u1 dot x1 is 0, u dot x2 is 0, u dot xk is 0 because of this property. So it's actually in fact equal to 0. So what does it tell you? That the length of the vector is 0. The length squared. And because the length squared is 0, the length is 0, and we know that the length is 0 if and only if we got the 0 vector. And we learned this from the length of a vector subsection, right? So that's the previous video. So yeah. So in conclusion, the only vector orthogonal to every vector in Rn is the 0 vector. That's the important conclusion of this example. So yeah, okay. Now we can discuss what is meant by an orthogonal set of vectors. A set of vectors. So we discussed what it means for two vectors to be orthogonal. Now we are going to describe what it means for a set of vectors to be orthogonal. But the idea is similar. It's just that if you choose any two different vectors, different or distinct vectors, so I cannot choose u1, u1. I cannot choose u2, u2. I can say u1 dot u2, u2 dot u3. Whenever I take two distinct different vectors, the dot product is going to be 0. And that's why I not equal to j means the indices, the subscript must not be the same. And also none of them are the 0 vector, because we just learned from this example that the 0 vector dot with anything is going to be the 0 vector, right? That's also a property that we learned under dot product. So yeah. So this is the definition of an orthogonal set. For an orthonormal set an orthonormal set satisfies everything that an orthogonal set satisfies. That means this too is true for orthonormal sets, but there's an additional property that all the vectors have to have length 1. So yeah, the length is always 1. And we get this definition from the fact that, okay, what happens if I is not equal to j? If I is not equal to j, then we know that ui dot uj is equal to 0, and that's from the definition of orthogonality. But what happens if I is equal to j? Then I have ui dot with ui, and under properties of dot product, we know that this is the length of ui squared. And because we want the length to be 1, this means that we have 1 squared and we have 1. So that's what this right here means. This is the Krochner delta notation, which we'll talk about later. Essentially, this tells us that if I is equal to j, we get 1. If I is not equal to j, we get 0. It's a short form notation for this. So it's a Krochner delta notation. But yeah, this is an R. But yeah, okay. So all orthonormal sets are orthogonal because like I said that if we take an orthonormal set and we normalize each vector so that they have length 1, the resulting set is called an orthonormal set of vectors. And we also went through the concept of normalization under these subsection involving lengths, right? So if you have a vector u, you would normalize a vector by dividing the vector u by the length of u. So that's how you normalize a vector. So that explains why all orthonormal sets are orthogonal, but the reverse is not true because some vectors may not be. Not every orthogonal set is orthonormal because some vectors may not have length 1. But in order to normalize the vectors, all you have to do is divide each one by its length. So normalizing a orthogonal set is the process of turning an orthogonal set into an orthonormal, orthogonal, and orthonormal sets. So let me repeat that again. Normalizing an orthogonal set, so a set that only satisfies these two conditions, would involve us with normalizing the set. So we would divide each vector by its own length in order to get an orthonormal set. So if u1, u2 up to uk is an orthogonal set, all we have to do is divide each vector by its own corresponding length and you will get an orthogonal set. So this tells you how to get an orthonormal set from an orthogonal set. Orthonormal and orthogonal. So let's go through an example to illustrate this concept. Consider the set of vectors given like this. We want to show it's orthogonal, right? And what does that mean? If it's orthogonal, condition 1 needs to be satisfied. That means for two different vectors, I need to show that the dot product is 0. We only have two vectors here, so I need to show that the first vector dot with the second vector is 0. And when we compute that, we have 1 times -1 plus 1 times 1, and that's -1 plus 1, that's 0. So the first condition is satisfied. The second condition tells us that none of the vectors are 0 vectors, and that's obvious from this example. But is it orthogonal? That's something orthonormal. We just check and we just proved that it's orthogonal. Is it orthonormal? That's something we have to check. And essentially, if I calculate the length of the first vector, I get square root 1 square plus 1 square, that's square root 2. The length of the second vector is going to be square root -1 square plus 1 square, that's square root 1 square plus 1 square, that's square root 2. So none of the lengths are 1. So we need to normalize this, and the idea is to divide each vector by its length. So the orthogonal set will be 1 over square root 2 times the vector, the first vector, then 1 over square root 2, which is also the length of the second vector, and -1, 1. So this would be the orthonormal set. So yeah. So this set is orthonormal. So a key theorem is that if you have an orthonormal set of vectors in Rn, this set is linearly independent And you can show that using it honestly just derives from this expression. The thing that makes orthogonal vectors so useful in like engineering or in physics is the fact that when you take a dot product of two of them, they are always it's zero. That means they're perpendicular. And you can make a connection with like the xy axis or the xyz axis you always draw in your graph, right? The axes are all 90 degrees to each other. So yeah. Okay. So yeah, okay. So the important thing is that orthonormal sets are linearly independent and they form a basis for the span of the same set. So they form a basis for all linear combinations of the set. Oh, so I wrote it down here. So yeah, okay, cool. And now I think this is the last thing for this subsection. If we have an orthogonal set, that's a basis, we call it the orthogonal basis. If we have an orthonormal set, we call it an orthonormal basis. So now we want to discuss something called Fourier coefficients, and this is linked to the part where we talked about projections in the previous section, where we talked about applications of dot product. So if you're given any orthogonal basis in Rn, we can express X, an arbitrary vector, any vector, as a linear combination of this orthogonal basis. And the idea is to project the basis, the vector, onto each basis. So we are doing projection. So the key idea is to project X onto each basis vector V2 up to UK. So let me just clear this. Oops. That's, yeah, this subsection. So remember, when we want to project the orthogonal projection of a vector u onto v is given by this formula. So now we want to project every x onto the basis element and we take the sum. That's essentially what's happening. So for example, this component, we are projecting x onto u1. So yeah. And this expression is called the Fourier expansion of x, and j equal 1 to up to m are the Fourier coefficients. So yeah. All right. So as an example, yeah, okay, let's go through this example. So let's say we have this orthogonal basis u1, u2, u3 given by these three vectors here, and we have vector x. I want to find the Fourier expansion of x. And by definition above, this expression is called the Fourier expression. But since we only have three vectors, I have the projection of x onto u1 plus times u1. So this entire thing is the projection of x onto u1. And then we have the projection of x onto u2, and we have the projection of x onto u3. There are only three vectors here because there are only three vectors on the basis. So this thing is the projection of x onto u1. This is the projection of x onto u2, and this is the projection of x onto u3. So yeah. Okay. And then you can see that's what's being done over here. All we do is copy paste the definitions, and then we have all the numbers over here. We just have to plug them in. For example, x is given by 1, 1, 1. u1 is given by 1, -2, 1, -1, 2. So we just take the dot product, which gives us 2. We calculate the length of u1, that gives us square root 6. So the length squared is just 6, and we just plug in the values. So yeah. That's how we calculate. That's how we get the Fourier expansion of a vector. And if you add all of this up, you should get back this vector here. So that's essentially, yeah. It's the same thing, it's just, you're just expressing it in a different basis. So yeah, okay. Now, now let's go to the next subsection. We are going to talk about orthogonal matrices. So we talked about orthogonal sets and orthonormal sets right now. So we're dealing with a set of vectors. Now we are going to deal with matrices which are orthogonal. But you'll see that the ideas between them are not too different. So the first paragraph just motivates why orthogonal matrices are useful. So orthogonal matrices actually have, if a matrix is orthogonal, it's really easy to calculate its inverse. If A is an orthogonal matrix, the transpose of A is going to be equal to the inverse. So yeah. That's how we actually define the orthogonal matrix here. So if you have a vector and the transpose of a vector, if you have a vector A which is n by n, its transpose, so A transpose is going to be equal to A inverse. And there are two things that we can do over here which are equivalent. I can multiply the expression on the left and on the right with A on the right side. So I can multiply matrix A on the right side. That would give me A, and that would lead to this expression here. So I would have A times A transpose equal to A times A inverse. A times A inverse, by definition of inverse matrices, is just the identity. But if I multiply A on the left, I would get A transpose A equal to A inverse A. That's also equal to the identity. So that's why we have two expressions. So we can either take U times U transpose or U transpose times U. It does not matter. So yeah, okay. So a matrix is called okay, so the reason why I'm saying this is because this definition here, from this statement, we can derive these two expressions, which is what the formal definition is. So usually when we want to do calculations and stuff, we're going to use these two here. If you want to check whether a matrix is orthogonal, we want to check if one of these conditions is true. Either this is equal to I or this is equal to I. You can pick either one. And as long as one of them is equal to I, the other is also equal to the identity matrix. So yeah. And we are going to do that right now. So let's say we have an orthogonal, let's say we have a matrix U. We want to show that this matrix is orthogonal. So we need to show that U times U transpose is 0. From this matrix, if I swap the rows and columns, I get the transpose of that matrix. And all we have to do is just some matrix multiplication. And this is simply from the definition. So yeah. And this example is also really similar. Matrix U, whether is this orthogonal, we first compute the transpose of the matrix, which is really easy. I just swap the rows with the columns, and then I'll perform matrix multiplication. And since the multiplication is equal to the identity matrix, my matrix U is orthogonal. So here we just want to apply what we learned under the ijth entry of a product. So in this subsection, what we did was we used the entries of a matrix to describe matrix multiplication. We went through this way earlier in the semester, and the idea is the same here. So if we take a row of a matrix, when we are taking the matrix multiplication of a matrix with its transpose, we are taking the row of the first matrix with the column of the second matrix, and we are multiplying them component-wise and summing up the components together. That's what's written over here. If that sounds like Rick to you, go to the other the subsection that I just showed you, this one, and refresh your memory. And let's see what happens if we take this multiplication. In this 2 by 2 example, my matrix A is given as A, B, C, D. So this matrix right here, this matrix right here is my A transpose. So what I'm computing is my A transpose. And we know that if A is orthogonal, then we have the identity matrix, right, being multiplied to each other. But what happens when we multiply this matrix together? My first row multiplies with the first column to give me my first element over here. My second row multiplies with the first column to give me this element right here. My first row multiplies with my second column to give me my this entry here, and then my second row multiplies with my second column to give me my last entry, and this is equal to the identity matrix, right? So we know that this is equal to 1, 0, 0, 1, and this gives us this algebraic identity. And this is what this is exactly saying. So yeah. And this is the Kroner symbol that we saw earlier on. So essentially what we are doing is we are rewriting the multiplication in terms of to relate it to the elements of a matrix, the elements of the matrix U itself. So in words, the product of what I explained so far can be succinctly seen over here. The product of the ith row of U with the kth row of kth row gives 1, because remember, when we take the columns of your transpose are exactly the rows of your actual matrix, right? Because my first row of my matrix A over here is AB. My first column of my transpose matrix is also AB. So essentially what I'm doing is I'm multiplying the first row of A with the first row of A. I'm multiplying the first row of A with the second row of A. I'm multiplying the second row of A with the first row of A. So I'm basically just multiplying the rows together. So that's what this is saying. If I'm multiplying the same rows together, I get 1. If I do not multiply the same rows together, I get 0. And this also holds true for columns, because I can apply the same argument to U transpose U. Not earlier on we applied it to U transpose. Now I'm applying it to U transpose U. So yeah. So essentially all this tells us, and this is where we make a connection to the orthogonal set and orthonormal set. What we have is we have the columns of the matrix U, right? They are orthogonal. So if you treat each column as a vector, so we are treating the columns as a vector, that set. So if I have this matrix U, which is the first column represented as U1, the second column represented as U2, and the last column represented as UN, each of this column can form a set of vectors, right? If I treat each column as a vector. This is also an orthogonal set. So here we are building the connection from an orthogonal matrix to an orthogonal set. So yeah. So the columns form an orthonormal set of vectors, and it's similar for the rows. So yeah. And this just tells you that the rows of an n by n orthogonal matrix forms a orthonormal basis for Rn. So yeah, that's an important theorem that you need to know. And I think this is the last part of this chapter. This is something important I wanted to talk about. Let's say U is an orthogonal matrix. Then by definition, we know that U transpose U is the identity. Now I want to show that the determinant of U is, what this means is that the determinant of U is either +1 or is always -1. It's one of this. It's either always +1 or always -1. And how do you prove this? Because we know that U transpose U is the identity, is equal to the identity, I applied the determinant on both sides. So that because U transpose U is the identity, the determinant of U transpose U is going to be the determinant of the identity, right? That's what my second statement says. And here I'm applying the theorem that we learned under determinants, that the determinant of AB is equal to determinant of A times determinant of B. And we know that the determinant of the identity matrix is 1. So we have the determinant of U transpose times the determinant of U is equal to 1. Okay? And what does this mean? This means that, and what do we know? We also know that the determinant of the transpose is equal to the determinant, right? So we know that the determinant of the transpose is equal to the determinant, because we can just choose a different row or a different column to compute that determinant. They are the same thing. So what we have is that the determinant U squared is 1, and this means that the determinant of U is either plus or minus 1. So yeah. And that tells us, that gives us the proof of this proposition. The next part just tells you that there are two classes of, we can categorize these orthogonal matrices according to what the determinant is, either +1 or -1, but that's not too important. And if you have matrices that are orthogonal, the multiplication of the matrix multiplication of two orthogonal matrix gives you an orthogonal matrix, and the inverse of an orthogonal matrix is an inverse. So this is wrong. Ignore this. This is incorrect. Ignore this. The key thing is that the multiplication of two orthogonal matrices is orthogonal, and the inverse of an orthogonal matrix is also orthogonal. So yeah. Okay, that's cool. And yeah, with that, we are done with this video. Again, if you have any questions or anything that's not clear, feel free to send me an email, or if you want to discuss your paper, your midterm paper, you can also send me an email and we can talk about it. Yeah.